Okay, hello everyone in a new video. So I have reached part 10 of chapter 8, which is the chapter of Newton's second law for rotation for grade 11 students. Now, as usual, always we refer to this table and different explanations and exercises. And now in this video we have reached, or this part we have reached section number 6, which is the parallel axis theorem. And this is also known for Huygens theorem. So suppose we have a disk D of radius r and of mass m. Let D be a disk of center O, radius r, and of mass m. Here for sure we are talking that the mass is homogeneous distributed uniformly around the disk. Now previously we have discussed what is meant by inertia, or specifically moment of inertia. It is the analogy of the quantity of mass but in rotation. In this case the moment of inertia around the center O is given by, if we refer to the table, so we are discussing the case of the disk passing through its center, which is given by half mr squared. This is suppose that the axis of rotation is passing through the center of the disk. But actually what will happen now is that we will define a point, any point here, say for example here on the disk. Let me take it to be an arbitrary point, not related to symmetry in any sense. And now the axis of rotation, which is delta, instead of being passing through the point O, now it will pass through the point A that is located at a distance d from the initial axis of rotation, or the symmetric one, which is at the center. So d is the distance between the points O and A, which is we expect to be given and can be measured in either case using a graduated ruler. So now we are interested in calculating the moment of inertia around the axis delta. So here you cannot say that the moment of inertia around the axis delta is simply given by I0 is equal to half mr squared, because this is very specific and it is in the case where the moment we are discussing the moment of inertia of a disk passing through the axis of rotation is passing through the center. So here it comes the parallel axis theorem. So apply, or according to the parallel axis theorem, so the moment of inertia around the axis delta, or for the system D, it will be simply the moment of inertia, let me say the moment of inertia at the point A is equal to the moment of inertia at the point O plus the mass of the disk multiplied by the distance d to the power 2. Now let me define what does each quantity represent. So d is the distance between O and A such that the moment of inertia at O is given which is I0. So the point O, or let me say the point O is usually taken to be the center of mass. So M is the mass of the disk. So in this case, if we know the moment of inertia at the point O, we can directly deduce the moment of inertia around the axis delta, because we know the moment of inertia at the point O, we know the mass of the disk, and we know the distance separating O and delta. For example, in this sense, here, if you consider the last two rows of this table, so in this case we have a rod in which the axis of rotation is passing through the rod, and we know that it's given by 1/12 ml squared. Now we can determine the moment of inertia of this rod around the axis of rotation passing at the edge of the rod, which is the peripheral or the extremity, by applying parallel axis theorem. So we want to prove that if this is 1 and this is 2, we want to prove that for 2 we have, so this is an exercise or an example, we have that I is given by 1/3 ml square, starting from the fact that the moment of inertia of the rod through an axis passing through its center is given by 1/12 ml square. So let me say that this is the point A and this is the point O. So now what's separating O and A is given by L divided by 2. So the moment of inertia at the point A is given the initial moment of inertia, not initial but the one corresponding passes through the center of mass, plus the mass of the rod, which is denoted by M, multiplied by D square. D in this case is given by OA, which is equal to L divided by 2. So now the value of I0, which is the initial 1/12 ml square, plus M multiplied by L L over 2 to the power 2. So this is equal to 1/12 plus ml square plus 1/4 ml square. So we can take ml square as a common factor. We are adding two fractions. So here if you multiply by 3, then it's given by 1 plus 3/12 ml square, which is equal to 4/12, which is 1/3. So in this case we have proved that the moment of inertia of the rod around an axis passing through its peripheral is given by 1/3 ml square, and this can be done for any shape and any point with respect to the moment of inertia that we usually know, which is passing through the center. So you can apply this to different shapes. Okay, and now let's consider the following exercise as a direct application. They are telling me in exercise 16, apply the parallel axis theorem to calculate the moment of inertia of disk about an axis delta. The moment of inertia of the disk about delta 0 is I0 is equal to half mr square. So we know that here now the axis of rotation, here there is no axis of rotation. We suppose that it might exist of axis of rotation, one around delta 0 and one around delta. We want to calculate the moment of inertia around the axis delta. Okay, knowing that around delta 0 is given by half mr square. So if you know delta 0, we can determine that of delta by simply applying parallel axis theorem. So apply parallel axis theorem. So notice that here they are being very specific, the moment of inertia of the disk about delta 0, and this is delta 0, but actually we are interested in calculating the moment of inertia of the disk about the axis delta, not delta 0. So we are interested in determining I delta, I delta is related to I delta 0 by the parallel axis theorem. So let me say here I0, and what relates both quantities is the following term, which is given by the mass of the disk multiplied by d to the power 2, in which d represents the distance separating I delta and I0. It's not separating I delta and I0, but which represents the separation of I delta and I0, because you know that these are quantities. They are not, they cannot be represented of the figure. So now in this case the distance is given by r. So I delta is equal to 1 over 2 m r square plus m. So I0 is given by this one, and mr square. So it's equal to 1 over 2 plus 1 multiplied by mr square, which is equal to 3 over 2 mr square. So in this case now we gain a new formula. You can add it in the previous table. So for example here you can add another row which corresponds to 3 over 2 mr square if the axis of rotation is passing through the peripheral of the disk. Okay, so for example here, if you have a disk that is hinged at this point here, and the disk, for example, if it is allowed to rotate like this, it's not working. If it's allowed to rotate around this axis delta like this, anti-clockwise, then its moment of inertia will be given by 3 over 2 r square. Okay. So this is it for the parallel axis theorem or Huygens theorem. So one should always be careful the location of the axis of rotation with respect to the center of mass. And now let's move to the following exercise, exercise number 17. A disk D of mass m is equal to 2 kilograms and radius r is equal to 20 centimeters. So the disk at our disposal is given by m is equal to 2 kilograms and the radius r is equal to 0.2 meters. Is free to rotate around a horizontal axis delta passing through its center O. So here, because the axis of rotation is passing through the center O, then okay, the moment of inertia is not given. Let's refer back to the table. Recall that the axis of rotation is passing through the center O. Then in this case the moment of inertia is simply given by this one. Okay, recall that this if the point is passing through the peripheral of the disk. So it's given by half mr square. In this case r represents the smaller radius. Disk D starts to rotate from rest, so the initial speed of this disk is given by omega 0, which is equal to 0. Under the action of a couple, so here we have a couple of forces, and indeed these two forces form a couple because both of them have the same line of action, opposite direction, and same magnitude. Apply tangentially to the disk. This is good. So whenever they are tangent in the tangential direction, no need for any projections. Taking this is the positive direction. I think that in the question they are taking this one to be the positive direction, but it's okay. So everything will be up to a minus plus sign. It's not important. Now the magnitude of one of the forces, F1 is equal to 10 newtons. So here let me say that we have a couple of forces. The couple, the distance d separating the couples is given by the diameter. So d is equal to 2r because the distance is important when calculating the moment. And here recall that whenever we are interested in the couple, we calculate the distance between the point of applications of the forces, because we are calculating the moment of a couple and not the moment between not the distance between the point of application of F1 and the axis of rotation. And in this case, we have that F1 is equal to F2 is equal to F, which is equal to 10 newtons. And recall that the moment of the couple, not the moment of a force. Let me recall the following. We have the terminology moment appear in several places: moment of a couple, moment of a force, and moment of inertia. Inertia means mass, couples mean two forces, moment of a force is just moment of a force. So here we are talking about the couple, which is the pair, which is simply F tangential multiplied by the distance d. D is the distance between the forces F1 and F2. Okay, that forms the couple. Now number one, name the forces acting on the disk. We have the force F1, F2. Now this is the axis of rotation. Because the disk has a mass, it will be subjected to the weight, which is vertically downward like this. So previously, in the previous exercises, we didn't discuss the weight, and now you will check why. And we have the reaction of the weight on the axis of rotation, which is like this. Now previously we didn't discuss the weight of the disk, but it is important that one should discuss the weight of the disk because it has a mass. So previously we didn't discuss the mass of the disk, and if we discuss, it is not of paramount importance, but now we should take it into consideration because I will discuss the pulley in the coming parts. So because it has a mass, then it will be directly subjected to the weight, and we have the reaction at the point O. Why the reaction here must be present? Let me explain. Now if there is no reaction and it is only subjected to the weight, this will make the disk to fall, will allow the disk to fall down. So in order to explain why the disk is not falling, we will introduce the reaction. It's very similar whenever we have a solid placed on a plane, it is subjected to the weight like this, then there is another force, which is the reaction force opposing the action of the weight. Now previously we didn't discuss the weight and the reaction in the case of moments because notice that the weight and the reaction, the line of action is passing through the axis of rotation, so it is not important for us. Okay, whenever we are discussing moment, but here I don't know in the exercise whether they will discuss rotational or translational equilibrium. Also another thing, whenever we used to consider a rod, I used to tell you that the reaction is not determined in which direction it is, but here because only we have one force trying to oppose the action of the reaction, so the weight. So usually the weight will be vertically downward like this and the reaction will be vertically upward like this, because this is exactly similar whenever we have an inclined, we have a plane and the weight is vertically downward like this and the reaction is upward like this. In other cases, whenever we have considered the beam to be like this, connected to the string here, to another string here, we weren't sure about the line of action and the direction of R because the problem is complicated. But in this case, whenever we have a disk subject under the action of its weight passing through O, so the reaction will cancel this weight like this. So we have the weight and we have the reaction R. Now in number 2, verify that the moment of the couple is 4 Newton per meter. So the moment of the couple. So here let me choose that this direction to be the positive direction, just to be in agreement with the question. Okay. So it is F tangential multiplied by the distance D. D is equal to 2R, which is equal to 2 times 0.2, which is given by 0.4. Now F tangential because it will try to rotate the system clockwise, and clockwise is chosen to be positive, so it's plus. F, no need for a cosine because it's completely in the tangential direction as mentioned in the text. So the moment of the couple is given by F times T, which is 10 multiplied by 0.4, which is equal to 40 Newton meter. So the moment of the couple is given by 40 Newtons meter. Now in number 3 they are telling me show that the angular acceleration of the disk is constant, and in order to determine the angular acceleration we need to refer to Newton's second law for rotation. So apply Newton's second law of rotation. And we have in this case the sum of moments is equal to I alpha. So what are the different moments acting on the disk? We have moment of the weight plus moment of the reaction, all of them around the axis delta, plus moment of the couple, which is equal to I alpha. Notice that here my notation is very specific. We didn't mention with respect to which delta, because the distance d is independent of the distance according with respect to delta, but rather the distance between the forces. Now this is 0, so let me say between brackets the moment of W around delta is equal to the moment of R around delta, which is equal to 0. Line of action of R and delta, sorry, R and W passes through delta. So for this reason, probably previously we didn't discuss anything about the action of the weight and R at the axis of rotation. Okay, but if you remember, in the case of the rod, we used to mention the weight of the rod and the reaction R. But I think there are one or two exercises that is related to the disk, and I didn't mention the weight and the reaction. Okay, it depends on the question itself. So this is 0, this is 0. Now we are interested in determining the value of alpha. So alpha is equal to the moment of the couple suppressed by the moment of inertia I. The moment of the couple is given by 4. Now regarding the moment of inertia is given by half mr squared. So this is I0. The moment of inertia is given by half mr squared, which is equal to half multiplied by the mass of the disk, which is 2, multiplied by the radius raised to the power 2. Let me calculate this value on the calculator. Which is given by 0.04 kilogram meter square. So the moment of inertia is equal to 0.04 kilogram meter square. Now 4 divided by the answer is given by 100, since everything in the SI. So the value of alpha will be expressed in the SI, which is radians per second square. So the angular acceleration of the disk is given by 100 radians per second square, which is somehow fast. And indeed it is a constant, so verified. And because we have done so, now we can directly deduce that the nature of motion is UVCM. Deduce the nature of motion of the disk. So it is UVCM verifies the general form alpha is equal to constant. And in this case we have two types of acceleration. We have the normal acceleration is always present, which is due to the change in direction of the velocity, and this is straightforward because the disk is under continuously circular motion. So if you consider the velocity at each point of the peripheral of the disk, then the direction of the velocity is changing, and now because also the speed is changing, we have the tangential acceleration, and this is straightforward because we have angular acceleration. Now in number 4, they are telling me the couple is applied on the disk for 2 seconds. So we have the time t. So now, after we have determined that alpha, the angular acceleration of the disk, is given by 100 radians per second square, and it's given by UVCM, we are free to use the following equations, that theta is equal to half alpha t square plus omega 0 t plus theta 0. What else? We have that omega is equal to alpha t plus omega 0, and alpha is equal to a constant, and omega 0 square final minus omega 0 square omega initial is equal to 2 alpha delta theta, and here delta theta is similar to the displacement that allows us to calculate the number of revolutions later. Now in number 4, the couple is applied on the disk for t is equal to 2 seconds, so the acceleration is given by t is equal to 2 seconds. Show that at the end of the 2 seconds the angular speed of becomes theta prime. Now the next section for me is to explain why they are denoting omega. So here the angular speed, one expect that it must be denoted by omega, but why they are denoting it by theta prime, in the next section I will explain why. So here let me now say that here they are asking about omega, which is the angular speed. Now in order to determine the angular speed, we need to refer to one of these equations. Since we have time, initial speed, and we are asked to calculate the final speed, so we will use this equation. So let me say that omega is equal to alpha t plus omega 0, and we need to calculate, so this is given by UVCM, and we are asked to calculate omega. So omega is simply hundred multiplied by 2 plus 0, because starting from rest, which is equal to 200, since everything in the SI, so this is radians per second, and indeed omega is given by 200 rad, which is radians per second. Now, so in a new phase, the motive couple is removed. These we call them motive couple because they are causing motion or rotation in the positive direction. Okay, and a braking force is applied on the disk to stop it during 5 seconds. So now a new phase, part 5, a new phase. So starting from the new phase, we have accelerated the disk, and we enter a new phase such that now in the new phase the initial speed is given by omega 0 is given by 200 radians per second. Now they are telling me the motive couple is removed and a braking force is applied on the disk. So we have a braking force. Let's represent this force to be something like this. Okay, it's acting opposite to the direction of motion. This is the braking force, and in translational motion this is referred to the friction force. So this is FB, representing the braking force opposite to the positive chosen direction. So we have FB, we don't know anything about FB yet, but the duration under which this force is applied is given by t is equal to 5 seconds. The moment of the braking force is constant, okay, and the motion of the disk during the braking phase is uniformly decelerated, which means also here we are in the case of UVCM. Calculate the angular acceleration of the disk braking, knowing that the initial angular speed in this phase is given, which is this. Okay, Later on I will explain why it's denoted by theta prime. Now let's take it to omega. So here they have specified the type of motion. Okay, so whenever they specify the type of motion, we can directly use the following equations. So since UVCM, we are allowed to use one of these equations. We are asked to calculate alpha. So alpha can be calculated either from the first equation or the final equation. Now this depends on the given. We have the time, we have the initial speed, and the final speed. Since they are telling us until the disk stops, so the final angular speed is given by 0. So we have initial and final, we have the time, we are asked to find alpha, so let's use the second equation. Omega is equal to alpha t plus omega 0, and we are interested in determining the value of alpha. Rearranging this equation, it's given by omega final minus omega initial, it's given by, divided by time, 0 minus 200 divided by 5, and this is given by minus 40 radians per second square, and the minus sign clarifies the fact that this is a braking force. Okay, and notice that although if you look at the problem from the following perspective, the disk started from rest. We accelerated the disk until it reaches an initial speed 200 radians per second, and then we have decelerated the disk until it reaches again back the initial speed, which is 0. But now the acceleration speed was the angular acceleration was given by 100. The angular deceleration is given by 40. The difference between 100 and 40 is that initially it took time 2 seconds to accelerate the disk from 0 to 200, while in the other part it took 5 seconds to decelerate the disk. For this reason, the angular deceleration is smaller in value. Now in part B, they are telling me deduce the value of the moment braking, and by deduce it means that we notice the previous part. In the previous part we have determined alpha, and we know that the moment and alpha are related via Newton's second law. So apply Newton's second law for rotation. We have the sum of moments around the axis delta is equal to I alpha. We have the moment due to the weight. We have the moment due to the reaction around the axis delta. We have the moment of the braking force around the axis delta. The moment of the attractive force or the motive force is now eliminated because it's not present anymore, which is equal to I alpha. And we are interested in determining the value of the moment of braking, which is this value. Okay, we are not asked to calculate the distance or the value of the magnitude of the force itself. This is 0 and this is 0 for the same reason. Now the moment of FB around delta is equal to I alpha. The moment of inertia of the disk, which is constant independent of the applied forces, is given by, oh, I have erased the value. Let me calculate it again. 0.5, I think it's given by 0.04 times 2 times the radius, which is 0.2 to the power 2. Okay, it's given by 0.04. So 0.04 multiplied by the value of alpha, which is minus 40. Now plugging this on the calculator, so it's given by minus 1.6 Newton meter. So notice that all of our results are reasonable. The moment of this force is smaller compared to the moment of the couple because it is taking the value of the acceleration is smaller, and the negative signs, it means that it's being applied in the negative direction. Okay, Now in part B they are telling us calculate the number of turns performed during the new phase, which is the stopping phase. Then we are interested in this one. First we need to calculate the displacement delta theta. So part C, we have omega square final minus omega square initial is equal to 2 alpha delta theta. Then delta theta is equal to omega square final minus omega square initial divided by 2 alpha. The initial final angular speed is 0. The initial one is given by 200 to the power 2 divided by 2 minus 40 on the calculator. So delta theta is equal to 500. Since everything is expressed in the SI, so delta theta will be expressed in the SI, which is radians. Now usually I always forget how to relate the number of revolutions by the number to the displacement, angular displacement. I think delta theta by 2 pi. Now, but we can always determine this using the rule of 3. If each one revolution or one rotation corresponds to 2 pi, which is 360 degrees, what about 500 radians corresponds to how many revolutions? This is delta theta. So n is equal to delta theta divided by 2 pi. So 500 divided by 2 pi revolutions. So n is equal to 500 over 2 pi revolutions. And now let me explain why. So this is it for this exercise. Now let me explain why. Let me explain the following note, which is extremely important. Why omega is denoted by theta prime, and also we have that alpha is denoted by theta double prime. Okay, so why this happens? Now let's recall a bit of units. So the unit of theta is given by radians. The unit of omega is given by radians per second, and the unit of alpha is radians per second square. So notice that here theta and omega can be related by an operator by a difference of second. So the operator that relates them is the derivative. So if you derive theta with respect to time, so the derivative of theta with respect to time is omega, and the derivative of theta with respect to time is denoted by d theta by dt. Usually in math this is denoted as dx, and this will be theta prime, which is omega. Okay, so what I mean is that if you derive theta prime with respect to time, we will obtain omega. So this is simply theta prime is equal to omega. Okay, now omega, the unit of omega is radians per second, and the unit of alpha is radians per second squared. It means that if you derive omega with respect to time, you will get alpha. So omega prime is equal to alpha. But we know that omega prime is simply theta prime. So now replacing this, but omega is theta prime. So omega prime is equal to omega prime, which is equal to theta prime prime, which is theta double prime, double derivative. So alpha is simply double derivative of theta. Okay, and this is obvious because if we are discussing UVCM. So here what I want to say, that we have theta, we can derive it once with respect to time, we can derive it twice with respect to time. This is angular position, this will be angular speed, this will be angular acceleration, If we are not talking about the derivatives, this is denoted by omega, this is denoted by alpha. Okay, and this is obvious because if we are talking about UVCM, we have alpha is equal to theta half alpha t square plus omega 0 t plus theta 0. Omega is equal to alpha t plus theta, omega 0, and alpha is equal to a constant. And if you apply derivative of this on both sides, this is theta prime gives you omega. The derivative of this is alpha t, and the derivative of the linear term is constant. Now if you derive once with respect to time, omega prime gives you alpha, the derivative of the linear term is constant, and this is 0. Okay, so that's it for me in this video, guys. In the next part, I'll explain what is meant by massless pulley, the difference between the massless pulley and the inextensible string, and we'll continue solving exercises on this chapter.